Hello viewers, welcome to the last section, Reconstructing 3D Scenes. In this section, we will look at calibrating a camera. Then we'll move on to recovering camera pose. After that, we will be reconstructing a 3D scene from calibrated cameras. Finally, we will learn computing depth from stereo image. Now we move on to the first video, calibrating a camera. In this video, we will use the chessboard pattern to generate the set of 3D scene, then specify the corresponding 3D points, and finally define the maximum number of iterations. Camera calibration is the process by which the different camera parameters are obtained. We can obviously use the specifications, but for some tasks, such as 3D reconstruction, these specifications are not accurate enough. By undertaking an appropriate camera calibration step, accurate calibration information can be obtained. An active camera calibration procedure will proceed by showing known patterns to the camera and analyzing the obtained images. An optimization process will then determine the optimal parameter values that explain the observations. This is a complex process that has been made easy by the availability of OpenCV calibration functions. OpenCV proposes that you use a chessboard pattern to generate the set of 3D scene points required for calibration. This pattern creates points at the corners of each square, and since this pattern is flat, we can freely assume that the board is located at z equal to 0, with x and y axis well aligned with the grid. So in this case, the calibration process simply consists of showing the chessboard pattern to the camera from different viewpoints. Here is one example of a calibration pattern image made of 7 by 5 inner corners as captured during the calibration steps. Now the good thing is that OpenCV has a function that automatically detects the corners of this chessboard pattern. For that, we have specified output vector of images in this line. You simply provide an image and the size of the chessboard used, which is the number of horizontal and vertical inner corner, which I have defined here. The function will then return the position of these chessboard corners on the image. If the function fails to find the pattern, then it simply returns false. For that, we have defined chessboard corner in this line of code. So the output parameter, which is image corners, will simply contain the pixel coordinates of the detected inner corners of the shown pattern. There is also a special function that draws the detected corners on the chessboard image with lines connecting them in a sequence, which I have defined here. So when you run your program in OpenCV, you will clearly see various images, detecting the points inside the chessboard corners. The lines that connect the points show the order in which the points are listed in the vector of detected image points. To perform a calibration, we now need to specify the corresponding 3D points. You can specify these points in the units of your choice. However, the simplest thing to do is to assume that each square represents one unit. In that case, the coordinates of the first point would be 0, 0, 0. The coordinates of the second point would be 1, 0, 0, and so on. The last point being located at 6, 4, 0. There is a total of 35 points in this pattern, which is too small to obtain an accurate calibration. To get more points, you need to show more images of the same calibration pattern from various points of view. The OpenCV calibration function assumes that the reference frame is fixed on the calibration pattern and will calculate the rotation and translation of the camera with respect to the reference frame. So in this case, the calibration process simply consists of showing the chessboard pattern to the camera from different viewpoints. Let's now encapsulate the calibration process in a camera calibrator class. The attributes of this class is highlighted here. Note that the input vectors of the scene and image points are in fact made of standard vector of point instances. Each vector element is a vector of the points from one view. Here, we decided to add the calibration points by specifying a vector of the chessboard image file name as input. The method will take care of extracting the point coordinates from these images, and that is defined in this block of code. So let's see what does this block of code do. These two lines will open the chessboard images and extract its corner points. Here, highlighted lines define the point on the chessboard. Here, the highlighted for loops are defined for 3D scene points, which will initialize the chessboard corners in the chessboard reference frame. The corners are at 3D location of x, y, z as I, j, and 0. For 2D points, we have defined this block of code. Here, the first loop inputs the 3D coordinates of the chessboard, and the corresponding image points are the ones provided by the CVFind chessboard corners function. This is done for all the available viewpoints. Moreover, in order to obtain a more accurate image point location, the CVCorner subpix function can be used, and as the name suggests, the image points will then be localized with subpixel accuracy. The termination criterion that is specified by the CV term criteria object defines the maximum number of iterations and the minimum accuracy of subpixel coordinates. These conditions, when reached, will stop the corner refinement process. So when a set of chessboard corners have been successfully detected, these points are added to our vectors of image and scene points using our add points method. Once a sufficient number of chessboard images have been processed, we can initiate the computation of the calibration parameters with highlighted block of code. In practice, 10 to 20 chessboard images are sufficient, but these must be taken from different viewpoints at different depths. The two important outputs of this function are the camera matrix and the distortion parameters. Let's now turn our attention to the distortion parameters. So far, we have mentioned that under the pinhole camera model, we can neglect the effect of the lens. However, this is only possible if the lens that is used to capture an image does not introduce important optical distortions. Unfortunately, this is not the case with lower quality lenses or with lenses that have a very short focal length. Even the lens we used in this experiment introduced some distortion. The edges of the rectangular board are curved in the image. This distortion becomes more important as we move away from the center of the image. This is a typical distortion observed with a fisheye lens, and it is called radial distortion. It is possible to compensate for these deformations by introducing an appropriate distortion model. The idea is to represent the distortions induced by a lens by a set of mathematical equations. Once established, these equations can then be reverted in order to undo the distortions visible on the image. Fortunately, the exact parameters of the transformation that will correct the distortions can be obtained together with the other camera parameters during the calibration phase. Once this is done, any image from the newly calibrated camera will be undistorted. Therefore, we have added an additional method to our calibration class, and that is given here. So to remove the distortion in this image after calibration, we have defined this function, and it will call once per calibration. And then we have applied the mapping function with this line of code. This flag is used for interpolation type. More options are available when it comes to camera calibration.